Why don't we get started? So where we last left off, we talked about growth functions, and we said a growth function, m sub h, it's indexed by the hypothesis set, and it has a parameter consisting of n, the data set size, the number of in-sample points. And we said it's the maximum number of dichotomies that you can form, labelings of +1, -1, that you can form over a data set of size big N. And we said that the growth function satisfies an upper bound of 2 to the n possible labelings. Okay. So then we talked about the growth function associated with increasingly complex hypothesis sets. We had the positive rays, and we reasoned about a quantity we called the breakpoint, which is a single number describing the size of the data set at which a particular hypothesis could no longer shatter that data set or produce all possible 2 to the n labelings. And so we looked at the positive rays, and we found that the breakpoint, or reasoned that the breakpoint was 2, breakpoint k. We looked at the positive intervals, and we found that the breakpoint for the hypothesis set of positive intervals was 3. And then we looked at convex sets which did not have a breakpoint, and therefore would say the breakpoint k for the set of hypotheses described by the convex sets is infinite. Okay. Then we said, and this was our primary result, if there's no breakpoint for a particular hypothesis set, it means that the growth function is exponential, or 2 to the n. It can produce all 2 to the n possible labelings of +1, -1 on your data set of size n. And then we said, using the union bound for Hoeffding's inequality, replacing the growth function for the hypothesis set complexity measure, big M, we said that if this growth function, or a breakpoint more specifically, is described as a polynomial expression, polynomial in the data set size, then generalization will occur and learning will happen. And the reason for that is that using the form of the union bound and substituting that polynomial growth function for our hypothesis set complexity, that decaying exponential in the union bound version of Hoeffding's inequality would suitably decay that complexity measure so that your probability was suitably small. Okay? All right. Any questions about this? Okay. So let's go on to this point, and the whole focus of today is this discussion about growth function being polynomial. And so we said more generally, in functional form, is the growth function polynomial, but now we're going to actually more rigorously prove that the growth function is polynomial. Now, of course, when we talked about growth functions, we had n sub h, and that growth function is indexed by the hypothesis set, and it's specific to the hypothesis set. But what we want is something more general than that. We want something that more generally will talk about the descriptive power, as it were, of our hypothesis set without necessarily being tied to the hypothesis set itself. And so the breakpoint gets to that, but we want to move away from this idea of using the specifics of the hypothesis set to talk about the descriptive power. So let's take a look at this. So we argued that our growth function, m sub h of n, is polynomial in n, the set size of our input set. And we're going to do this by proving a bound. And we're going to show that that upper bound on the growth function is itself polynomial. And if the upper bound is polynomial, then the growth function itself is also polynomial. So that's going to be the approach that we're going to take. So in order to show that something is polynomial, our growth function, polynomial in our input set size, we're going to show that it's at most something, at most something, at most something that is itself a polynomial. And so that quantity of interest is we're going to wind up with the recurrence relation, and then we're going to solve that recurrence relation in closed form and show that that solution is polynomial in n, the input size. And so that quantity is called b of nk. You could call it the breakpoint function, if you will. And b of nk is described as the maximum number of dichotomies that a hypothesis set can form on n data points, given that it has a breakpoint k, right? Now you notice here this doesn't say anything at all about the specific hypothesis. It doesn't say the positive ray, it doesn't say the positive interval, it doesn't say convex sets. It's a purely combinatorial argument. And this is going back to what I mentioned about this idea of growth functions, that when we make a purely combinatorial argument in terms of the descriptive power of the hypothesis set, when we do that purely from the in-sample points, now we can relax or move away from this idea of a specific hypothesis set. Now, what we saw earlier is when we had the positive ray and we had the positive interval, we had to very diligently count all the different possible dichotomies it can form. Now, of course, it's easy to do with those very simple example functions, but it's really, really hard to do with an arbitrary hypothesis set, right? So imagine if someone were to say the set of degree 100 polynomials, right? What's the growth function of that? I don't know. How do you count that? So we need a way that's separated or divorced, if you will, from the specific hypothesis set. And we're going to use a combinatorial argument and develop that and show that this is polynomial in its upper bound. So we make no reference to our hypothesis set, and we also make no reference to input space or feature space. And so we're kind of not talking about the dimensionality of the feature space, and therefore we're not talking about the dimensionality of the learning model. Okay. So because it's combinatorial, this gives us a convenience, if it will, or as it were, it makes it convenient for us to come up with a closed form expression that we can solve for precisely. Okay. So I'm going to spend a lot of time on this diagram because there are a lot of moving parts in it, and I want to make sure that's understandable. Okay. So here we have a data set, and this data set is along the columns here. We have x1, x2, x3, and so forth, up to and including x sub n. So we have a data set of size n labeling the columns. Now, associated with each data point in our data set of size n is going to be a labeling drawn from the class labels +1 or -1, right? And so each row here in this table, for example, this first row, that's going to be one assignment of +1 or -1, i.e. a dichotomy, to each of our n many data points, right? And so looking at each of the rows, we have an enumeration, and we can certainly count all the possible labelings we can associate with this data set of size n. Does that make sense? Okay, so if we were to count the number of rows in this table, essentially we're counting the number of dichotomies that are associated with a data set of size n. Now, in this first column here, we have some names, and those are just going to help us identify certain stylized patterns associated with subsets of this dichotomy. And we're going to use subsets of this possible set of dichotomies to define or help us define a recurrence relation that we're going to bound from above and show that it's polynomial. Okay? All right. So let's start out. We're going to list out in this table all of the patterns up to the breakpoint. Now remember, the breakpoint describes the maximum data set size at which a function or hypothesis can no longer generate all 2 to the n dichotomies. So if we were to define b of nk, well, the n corresponds to the data set size here. So you're going to have n columns corresponding to x1, x2, all the way up to and including x sub n. And then the k part talks about the breakpoint. And there's going to be a direct relationship between the breakpoint k and the number of rows in this table. Because the number of rows in this table is going to be something less than or equal to 2 to the k, right? Because breakpoint by definition is going to be that data set size such that the function can no longer generate all possible 2 to the k dichotomies. Does that make sense? Okay, so we have a data set of size n, and we have a breakpoint. And so let's define the different regions of this particular table. So we have the first region, and I'll just kind of isolate them here on the right. And that first region has a name, and that set name is called S1, right? And S1 is specifically defined as all of those dichotomies or patterns of +1 and -1 that are unique, right? So if you had a data set, it doesn't matter how big that data set is, you can take all the dichotomies associated with that data set of size n. It doesn't matter, without loss of generality. It doesn't matter what order they're in. You can put these data sets, these data points in some ordering, and then assign +1, -1 labelings to them. So you have all the dichotomies that are associated with a data set, given that the breakpoint is k, and you have n many data points. Now, among those dichotomies, you can find unique ones, right? And they are unique, and in this particular example, we're going to find those that are unique in the first n-1 data points. Now, if the pattern of ones and -1s is unique in the first n-1 data points, well, it doesn't matter what this nth labeling is for that nth data point. It's going to be unique for all n positions. Does that make sense? Yeah. Okay. So now we're going to call the set of all of those unique dichotomies, all those unique labelings, we're going to call that set collectively. It doesn't matter what the specific dichotomies are, but we know that we can find some unique ones. Sometimes that set S1 might be empty set. Other times it might be non-empty. But such a set exists, and we're going to call that S1. Okay? All right. So the size of S1, the number of dichotomies in that set S1, we're going to call alpha. So alpha is going to be the size or the count of the number of unique dichotomies associated with a data set of size n given a breakpoint of k. Okay? All right. So now the other dichotomies that we have, if we have S1 as the set of unique dichotomies, that means everything that's not in S1 is non-unique, right? And so the way we're going to define this is that there are some dichotomies that are the same in the first n-1 positions, and the only thing that makes them different is that you have a +1 in the nth position in one version, and you have a -1 in the position in the other version. And so in the first case, S1, that is unique. It only exists once, that dichotomy, right? Among all the dichotomies. You collect them all into S1, but for S2 plus and S2 minus, those are all the dichotomies that are not unique in the first n-1 positions. Does that make sense? Okay, so now we have in S2 plus, we're going to associate those non-unique dichotomies in the first n-1 positions. Those that have a +1 in the nth position, we're going to put in a set we call S2 plus. And those that are different in that last position as having a -1, we're going to put together in the set S2 minus. So for everything we have in S2 plus, there's going to be one that's the same in the first n-1 digits in S2 minus, and the difference is just going to be, here we have a plus, here we have a minus in that nth position. Okay, so the size of S2 plus, we're going to call beta, right? Now, by definition, the number of dichotomies in S2 plus is going to be equal to the number of dichotomies in S2 minus, because you have to have one. If you have one in S2 plus, you're going to have a similar one in S2 minus. There's a one-to-one mapping there. Okay, so here, if we were to look and count the total number of dichotomies given a data set of size n and a breakpoint of k, we're just going to sum all of these together. We're going to sum the alpha plus beta, and so our expression for b and k is going to be equal to alpha plus 2 beta. Does that make sense? Okay, so now we're going to kind of go into this recurrence, and we're going to reason based on this assumption and this structure that we put in place for this association or grouping. Now, mind you, this is theoretical. It's a combinatorial argument. So if you had 3 data points, you might not be able, S1 might be empty set. If you had 4 data points, S1 is most likely not empty, right? But nonetheless, this is how we're going to arrange them, and we're going to use the bounds on this idea of the max number of dichotomies given a data set of size n and a breakpoint k to show you how big the entries can get. okay, how many entries we can have. So this gives us an expression for BNK. And BNK, by this definition and this grouping, is alpha plus 2 beta. Okay. So now what we're going to do is we're going to now focus on the first n minus 1 positions of this table. And we're going to look at the maximum size in terms of the counts of all of those dichotomies that are represented if we only consider not the first n positions, but the first n minus 1 positions. So certainly that's going to kind of be a subset of the original one, because the original one, we counted all the dichotomies in the table. But the next one, right, is going to be something that we compose together with other parts of this table to form the full table, right? And that's what we're going to use to develop this recurrence relation. Okay, so if we strike out that last column, right, and we remove that from consideration, we still have a dichotomy, a set of dichotomies, but it's unique patterns of +1 and -1 from the perspective of a data set of size n minus 1. Now, the breakpoint hasn't changed, but when we talk about dichotomy, what we refer to is unique patterns of +1 and -1. And so by our definition, we said S2 plus, that region, and S2 minus, they differ only by that nth position. And therefore, if you're not considering that nth column, you can only have one copy. So we're just going to not include S2 minus. We're just going to count as unique dichotomies, labelings of +1 and -1 for n minus 1 positions. We're only going to count the dichotomies that were from S1, which were unique, and S2 plus, and it didn't matter if we picked S2 plus or S2 minus, but in this convention, because it mirrors the book, I'm going to pick S2 plus, okay? All right, so what does this represent? Well, we know that if we were to count the number of dichotomies in these n minus 1 positions corresponding to these labelings of n minus 1 data points, well, that's just alpha plus beta. Well, that's certainly the size. But how big can alpha plus beta get? Well, using this recurrence relation, well, the breakpoint didn't change, okay? But what has changed is the data set size. And so alpha plus beta is going to be at most the maximum number of dichotomies that you can have for a data set of size n minus 1, because we've removed now from consideration that position n, but our breakpoint has not changed. And so we know that it's less than equal to, but we just don't know if it's very close to be of n minus 1k, or if it's a little bit further away. But we know it can be no bigger than the number of dichotomies given a breakpoint of k that you'd have with a data set of size n minus 1. Does that make sense? Okay, so now that we've done that, let's now look at one of these regions. And we're going to focus on those portions of this table, the set of dichotomies, that focuses just on the non-unique elements. And so this is going to be S2, and S2 is going to be the union of S2 plus and S2 minus. We had said from before that the number of dichotomies in each one of these regions is beta, right? And we said that everything that's in S2 plus is also in S2 minus from the perspective of the first n minus 1 positions. And so if we were to look at this region S2 plus, and because it's the same size, it's also the size of S2 minus, let's look at the size of this. Now the size of this, well, certainly, if we look at the data set size, well, because we're considering n minus 1 positions for n minus 1 data points, well, the data set size is of size n minus 1, absolutely. But if we look at the breakpoint, something changes, something happens. The breakpoint decreases, and I'll prove to you why that breakpoint decreases. So if the breakpoint were k, right, for this region S2, well, if the breakpoint were k, and we were going to count these s's, well, what would happen? Well, we have a version here where this last position is +1. We have a version where it's -1, right? And so if you have a +1 extension on these n-1 labelings in the dichotomy, and then you have a -1 extension, well, that corresponds to increasing the breakpoint by 1, right? Because if you considered an example where if you had x1, x2, and you were to produce all possible labelings, minus, 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 plus, plus, minus, plus, plus, if you had another version of this down below, minus, 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 plus, plus, minus, plus, plus, if you have another position whose alternatives are minus or plus, well, you could call all of these minus, all of these plus, and now you've increased the breakpoint, okay? And so the reason this has to be k minus 1 is because if it were k, you would violate the original statement of b of nk is equal to alpha plus 2 beta. So it has to be 1 less, has to be k minus 1. Okay, does that make sense? All right, so we have a bunch of expressions here. We have an original expression using equality that talks about the number of dichotomies that you can form using n data points and a breakpoint of k. We talked about an upper bound on the size of the S of S1 and S2 plus region. We talked about an upper bound, now this last point, on the size of the S2 plus region, which is the same size as the S2 minus region. Okay, so let's take all of these quantities in our recurrence relation, and we're going to put them together, and something interesting will happen. So if we know that b of nk is equal to alpha plus 2 beta, well, alpha plus 2 beta is the same as alpha plus beta, right? So we know alpha plus beta, that's less than b of n minus 1 comma k, and then we know this beta is less than this b of n minus 1 k minus 1. So we can actually replace this expression with b of nk is less than, using those substitutions, the sum of b of n minus 1k plus b of n minus 1 k minus 1. It's just a substitution using this construction and the recurrence relations that we've developed. Any questions about this? Make sense? Okay, so why did I do this? Well, now we have an expression here, and this expression relates the number of dichotomies for a data set of size n given a breakpoint of k with the number of dichotomies for a smaller version, n minus 1 with the same breakpoint, n minus 1 with the smaller breakpoint. Okay, so we're going to use this recurrence relation, and we're going to do a little bit of manipulation, a little bit of reasoning, and we're going to come up with an expression that will demonstrate is polynomial. Okay, and again, this less than equal to is on purpose because remember, this is an upper bound. And if we can show the upper bound is polynomial, we can show that b and k is also polynomial. Okay, all right. So let's look at this expression. And we're going to start with the boundary values, and then we're going to reason from that using this recurrence relation, and it fits really nicely, and we can do this graphically, but then we're also going to do it mathematically as well. Okay, so let's take a look at this corner element here. So this says I have a data set of size 1, and I have a breakpoint of k. So if I have one data point, and this function or whatever hypothesis we have, it doesn't matter really what it is, it can no longer generate all possible dichotomies once the data set is of size 1. Well, what does that mean? I have one data point, I'll call it x, it's vector valued, and you can either make it +1 or -1. I can make it +1, but it can't do the -1 because it falls short of all 2 to the n possible dichotomies. So if you have one data point, 2 to the 1 is equal to 2, that means it can't generate 2 dichotomies using a data set of size 1. So that means the number of dichotomies it can generate is just 1, right? So that's where our 1 comes from. That fits into this b and k. Okay, let's look at the other alternative. The breakpoint is 2, k is 2, given a data set of size 1. That means once our data set goes to size 2, we can no longer generate all 2 to the 2 dichotomies. Well, 2 to the 2 is equal to 4, so that means it can no longer generate 4 dichotomies. Well, if you have one data point, well, what can you generate? You can generate the plus label or the minus label. So that means the number of dichotomies from a data set of size 1, given a breakpoint of 2, is going to be 2, and we write 2 here. Now, certainly, if the breakpoint is 1, it doesn't matter, it's vacuously true, that if the breakpoint is 1, you can only have one label regardless of how big the data set is. So we write 1s all the way down there. And that's the same if you have a data set of size, say, x1 and x2, data set of size 2. There's 1, there's 2. If your breakpoint is 1, that means you can't generate 2 labelings. So that means you're only going to have one labeling. Maybe that labeling is plus and plus, for example, right? And so that's vacuously true. So we write 1s all the way down, and we write 1 here, 2 here, and you get 2s all the way across, right? Given a data set of size 1, you can only have 2 labelings regardless of what the data set size is. Does that make sense? So the interesting part about this recurrence relation, it certainly works for the boundary values. And like any sort of proof, you start with the boundary values. You want to test it for, assume that it works for the assumption step. And then for the inductive step, you show it works for the next update, right? But the interesting part is, if we look at this recurrence relation, there's a relationship between b and k, bn minus 1, everything on the left of the inequality, and everything on the right of the inequality. So if we look at this relationship, well, if this is b and k, this value is 1 higher, that's b of n minus 1, because n changes as you go up, n minus 1 comma k. And then here, you're going 1 to the left, that means k is getting 1 smaller. This value is b of n minus 1 comma k minus 1. So you can literally take this structure, knowing that the base case works, and then here, this is just going to be 1 plus 2, which is 3. So we can absolutely test this out. Don't take it for granted, but just actually test it out. So let's look what happens for this case. For this case, it says the breakpoint is 2, and it says the data set is of size 2. What does that mean? I have 2 data points, x1 and x2. And the breakpoint of 2 means that once I have a data set of size 2, it can no longer generate all 2 to the 2 or 4 dichotomies. And so if it can't generate all 4 dichotomies, the maximum way it can generate less than 4 dichotomies is to generate 3 dichotomies. So that means for 2 points, x1 and x2, maybe it can generate a minus minus, a minus plus, plus minus, but not that last one. It can only generate 3. So the maximum way you can generate dichotomies with a breakpoint of 4 is to generate 3 different dichotomies. And so we get 3 here. And that also verifies, we did that through verification, this recurrence relation. That's the same as saying 1 plus 2 gives us that 3. Does that make sense? Okay, so let's try that here in the adjacent cell. The breakpoint is going to be 3, and the data set size is going to be 2. So that means we have 2 data points, x1 and x2, right? And our breakpoint is 3. So that means you can't generate more than 2 to the 3 dichotomies, which is 8. But you only have 2 points. So that means the maximum way for a data set of size 2 that you can just stop just shy of generating 8 dichotomies is all 4 of these dichotomies. Minus, 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 plus, plus, minus, plus, plus. That's 1, 2, 3, 4 dichotomies. And we have 4 here. Okay? And just so happens, if we were using the recurrence relation, we have 2 plus 2 is equal to 4. Okay? And so we can do this and fill in this table arbitrarily using this dichotomy. We've shown that it works for the base cases, And we showed through the exhaustive counting and reasoning that this dichotomy holds true. Okay? Now here, this entry is interesting. So here we have a data set of size 3, and we have a breakpoint of 2. So that means you can no longer generate 2 to the 2 dichotomies. Okay, so let's see what this looks like. We have x1, we have x2, we have x3 as our data set. Now this is where it gets a little bit interesting. If your breakpoint is 2, that means after a data set of size 2, you can no longer generate all 2 to the 2 or 4 dichotomies. So it would think that, all right, well, that means I can only generate 3 dichotomies. Minus, 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 plus, plus, minus, and that's it. But the issue is this is left free, right? And you have to have some labeling for it. Now, if you have to have some labeling for it, the labeling for this third one keeps. So if this last one can be 0 or 1, right? If the choice for 0 is 0 here, minus 1, minus 1, minus 1 here, you still have to have the case where this third one can be plus. And if this third one is a plus, you need something else here for the other 2. And that results in a total of 1, 2, 3, 4 dichotomies. Okay. And so that's a weird case, but you can actually verify that numerically by just counting dichotomies. And it gets really, as you've seen, it gets really strange as you get these vacuous cases. But nonetheless, if we use our recurrence relation, we have 1 plus 3 is equal to 4. And we can actually numerically count them or use the recurrence. Does that make sense? Okay, so now we have a recursive approach that we can use to define a bound on the maximum number of dichotomies given a data set of size n and a breakpoint of k. All right, so let's take a look at an analytic solution. And what we're going to do for this analytic solution, well, there's the answer, right? And we're going to show how we get to that answer mathematically, okay? And so it says that B n k, the maximum number of dichotomies given a data set of size n and a breakpoint of k, is going to be, at most, this summation of n choose I, for I goes from 0 to k minus 1. So we have our parameter n here, and n is going to be in that combination. And our parameter k here is going to be the upper index, or bound, if you will, in that summation. Okay? All right. So let's develop this. All right. So it works for any hypothesis with a breakpoint of k. And of course, if we're going to prove this, we need to start with the boundary conditions. And the boundary conditions are n equals 1 and k equals 1. That's exactly this position here. So if we take that expression, well, if we say b of n equals 1 and k equals 1, that's less than equal to the sum. I goes from 0, well, k is 1, 0 to 0, of n, which is 1, choose I, right? Well, you only have one term. That's just 1 choose 0. Anything choose 0 is just 1. Well, that checks out. Okay, great. So you start with the boundary value conditions and you demonstrate that it holds true. It does hold true. So now, if we want to prove this, we assume it works for the base case, and then we show that it works for the inductive step. Okay, well, to show for the inductive step, well, we already did that last time. We're actually showing what happens here, right, for these cases, and we show what happens here, and we show what happens here, which I won't repeat since we already did that. But nonetheless, you show it works for the base case, you assume it works for the typical case, and then you show the inductive step, right? And so you do that, you will definitely fill in these examples, and you see you get a 3 here, and so forth. Now, of course, if we said 2 and 2 here, right, just for the sake of completing this thought, b of n equals 2 and k equals 2, keep running to write k, is less than equal to the sum for I goes from 0 to k minus 1 is 1. And then we have 2 choose I. All right, so that's going to be 2 choose 0 plus 2 choose 1. So 2 choose 0 plus 2 choose 1. Well, 2 choose 0 is just 1. 2 choose 1 is 2. 1 plus 2 equals 3. Guess what? It matches exactly what we had from before when we had the combinatorial argument there, right? Okay, so we know it works for the base case, and we've shown that it works for the inductive case, this equivalence. And so, all right, well, yeah, then it must hold true. So now we're going to, does that make sense? The recurrence? And so we had this answer, and we wanted to show that this holds true. So by induction, we first showed that it works for the base case. The base case is for k equals 1 and n equals 1. And we tried this relation, right? And that gave us this n, this 1 choose 0, which is just 1. And then we assumed that it worked for the typical case. And then by induction, we looked at the inductive case. And so for the inductive case, we consider this position here 2, 2, right? And we said, all right, if we write in b of 2, comma 2, where n equals 2 and k equals 2, that's just less than equal to the sum. I goes from 0, k minus 1 is 1, of 2 choose I, right? And so if you do that sum, that's 2 choose 0 plus 2 choose 1, which is this 1 plus 2, which is equal to 3, right? And so we've shown it works for the inductive step. And so all that's needed for proof by induction is to show for the base case, you assume it works for typical case, and then you show the next step, the inductive case, to show that the recurrence relation holds true, okay? So absolutely, this b of nk is bounded from above by this sum for I goes from 0 to k minus 1 of n choose I, okay? So now we're going to show that this expression is polynomial. And this is where I'm going to kind of take a little bit longer time to show each of these steps. And so when you are trying to solve for this n choose I, go back, the sum for I goes from 0 to k minus 1 of n choose I, well, that's the same as saying n minus 1 choose I plus n minus, where'd it go? Okay, my mistake. All right, now I just lost my place. There we go. Let me start over. So we have our recurrence relation, right? And we have this n choose I, and this is going to be our b of nk, because our b of nk, it says a summation of k goes from I goes from 0 to k minus 1, n choose I, right? And so how we define this recursively is we reevaluate this b of nk, but we're changing the variables to n minus 1 and k in this case, and we're adding to that an evaluation of this recurrence, substituting the parameters n minus 1 and k minus 1. So if we have this expression for b of nk, it says you write the summation, but when you write the summation, you're going to write it substituting n minus 1 here. So you're going to substitute this summation, and you're going to write n minus 1 choose I and k minus 1 up here. It's just plugging in the expression for that recurrence. And then here, you're going to have another sum. And because you're passing the parameter n minus 1, you're going to have an n minus 1 here. But here, because it's k minus 1, k minus 2 here, because you subtract for whatever k is, subtract 1. And then you're going to say I, right? Does that make sense? Okay. So in this expression, we're going to write, using that recurrence relation, a definition for what that sum is. And so we have the sum, I goes from 0 to k minus 1 of n choose I, is equal to I goes from 0 to k minus 1 of n minus 1 choose I. That's for the b of n minus 1 comma k term. And then we have the sum I goes from 0 to k minus 2 of n minus 1 choose I. And that's an expression for the recurrence relation using these parameters from the b of n minus 1 comma k minus 1 term. Does that make sense? Okay, so now with this expression, we're going to do a little bit of manipulation, and we'll show in closed form solution, we'll get a result which is equal to the original sum, and then show that that is in fact a polynomial. Okay, so let's begin. So the first thing we notice here, this term, the left-hand sum, right? If I evaluate the summation at I equals 0, well, that's just n minus 1 choose 0. There's only one way to do that. So if I just rewrite that, I get the n minus 1 choose 0. That's equal to 1. And so the remaining terms in the summation, I have the sum for I goes from 1 to k minus 1, but then I write that n minus 1 choose 0 term right here, right? So I'm just kind of peeling off, if you will, that first term in the sum, and just the rest of that summed set of terms for I goes from 1 to k minus 1 still remain, and I have that expression, okay? So the second term here, notice what I'm trying to do is I'm trying to get the indices for both of these summations to be the same because I want to combine them, right? And so one way I can combine them is to have a change of index variable. Now, of course, in the book and in the video, when they change the index variable, they change it to the same name, which is kind of unfortunate, right? I always used to hate that when I was an undergrad. So I could say, okay, let's imagine instead of using I called it J, right? And I said, wherever I is, J is going to be 1 more than that. So I can start this index, I is 0, so J is going to be 1. And if it goes all the way up to k minus 2 when it was I, when it's J, I call it k minus 1, because k minus 2 plus 1 is going to be k minus 1. So now when I have this combination that's n minus 1, and now I'm going to say J, right? Okay. Now, the relationship between J and I, J is equal to I minus 1. So now, if I switched it back from J to I, right, I could write, well, I equals 1, but here, to make it the same expression, I have to say I minus 1, because it matters here what it is. Does that make sense? So that's what they do from the first step here for the second term down to that next line. And so if I do those two things, I'm left with 3 terms. I have 1 plus a summation, n minus 1 choose I, sum, for I goes from 1 to k minus 1. And then I have n minus 1 choose I minus 1, the sum, I goes from 1 to k minus 1. So now my indices for the summations are the same, and that's going to allow me to combine them. Okay, so let me do that. Now, of course, summation is associative. I can sum first under the summation and then add those 2 terms, or I can add the 2 terms first and then do those summations. And I can do that because they now have the same number of terms under the summation symbol. So I'm going to associate this n minus 1 choose I and n minus 1 choose I minus 1 first in a summation, and then I'm going to put them under the same summation symbol. So I have 1, that 1 didn't go away, and I have I goes from 1 to k minus 1, and I have quantity n minus 1 choose I plus n minus 1 choose I minus 1. Okay, now, of course, mathematically and algebraically, you could actually write out the expressions for n minus 1 choose I, write out the expression for n minus 1 choose I minus 1. You do a lot of calculation, and you get the equivalent expression is n choose I, right? Another way to reason over that, because I don't want to do all the writing out here, and I'm sure I'd probably make an algebra mistake, but when you think about when you're choosing something, suppose I had n objects, and let's say I wanted to choose 10 of those n objects. One way, let's say people, right? So we were in an auditorium, and I was in the auditorium too. One way I could say, how do you choose 10 people out of 10 individuals, a group of 10 people out of all the people that are in the auditorium? Well, one way I could do it is I would say, choose 10 people, including me, plus choose 10 people, excluding me, right? And that's the same as n choose 10, because the 10 that I choose could include me, or the 10 that I choose could exclude me, right? So if I choose 10, including me, right, that means I take n and I pick those 10 people, okay? And I'm one of the people that could be chosen. If I say choose 10 excluding me, right, then, I'm sorry, including me, that means I'm one of those 10. So that means I'm going to take the n and I'm only going to pick 9 people, right? Because one of those choices includes me. It has to include me. And then in the other case, if I say excluding me, I'm going to have that same pool. Well, that pool is decreased now. And I'm going to choose all 10, right? So that's just a roundabout way of saying that this is like saying choose 10 where I am a consideration, where I'm not a where I'm one of the people who can be. No, this has been a long day. This is like choose. This is like choose 10 people, including me as one of the choices, and this is choose 10 people, excluding me. I probably got that backwards. No, this is choose including me, because you only have 9 people you can choose, and this is excluding me. Okay, good. So we can take this expression and we can combine that into n choose I, right? Now, certainly, in about 5-10 minutes, you could write n minus 1 factorial over n minus 1 minus I factorial over I factorial, and you write the other term, and then you start canceling, and it would take you a long time. But you can use that reasoning, and it comes upon the same results. Okay, so now we have this expression, 1 plus the summation n choose I, which is the equivalent expression combining these two terms. I goes from 1 to k minus 1. And now we can go back, and another way of saying 1 is saying n choose 0, right? And we combine that under the summation. Our index changes. I goes to 0 as our starting index to k minus 1, summation for n choose I. And it's exactly what we started out here in the beginning. So yes, absolutely, this is a sound solution, and that is the expression for our function b nk. Now, absolutely, we've shown this, that the recurrence relation really does work using our original expression, our upper bound. Let's show that it's polynomial. Okay, so if we know that our growth function is bounded from above, and this is using a purely combinatorial argument, is bounded from above by the summation I goes from 0 to k minus 1 of n choose I. Let's consider the largest term in this summation. The largest term in this summation is going to occur when I equals k minus 1. And when I equals k minus 1, we have n choose k minus 1. Well, what does n choose k minus 1 look like? Well, it looks like n factorial over n minus k plus 1, so it's minus n minus quantity k minus 1, which is n minus k plus 1, quantity factorial, over k minus 1 factorial, right? And so what dominates this expression is the relationship between n factorial and n minus k plus 1 factorial, right? So let's consider this portion of the expression. So we have an n times n minus 1 times n minus 2, dot, dot, dot. At some point, we're going to have n minus k plus 2, and then we're going to have n minus k plus 1, dot, 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 times 2 times 1, right, in the numerator. In the denominator, we're going to have n minus k plus 1 factorial. Now, if we look at these terms, well, that's exactly n minus k plus 1 factorial. So those are going to cancel, it goes to 1, and now we're left with n times n minus 1, n minus 2, blah, blah, blah. Well, how many terms is that? Well, that's a total of k minus 1 terms. Now, of course, if we multiply these out as a polynomial, the first thing we're going to do is we're going to multiply n times n times n times n times n times n times n, k minus 1 many times. And the resulting polynomial that we're left with, the highest order degree, or the highest order power, is going to be n to the k minus 1 power. Okay? And so that shows, and it doesn't matter what the other terms are, right? Because you're going to have some a times n to the k minus 1 plus b times n to the k minus 2, and so forth. It doesn't matter what the low order terms are. What matters is what the highest order term is for that polynomial. So absolutely, this is going to be a polynomial, and in fact, the degree of that polynomial is going to be a degree k minus 1 polynomial, which is in fact polynomial. Now, the good news is that you notice here, k is a constant. It's the breakpoint. It's a defined number that remains constant. K does not vary as a function of the data set size. So it is a good, honest-to-goodness polynomial. And therefore, we've shown that this growth function is bounded from above by a polynomial. And therefore, we have a polynomial number of dichotomies. And if we have a polynomial number of dichotomies, that means the expressiveness of this function, this complexity, if we replace this growth function in Herfting's inequality, it was 2, and then we're going to replace m script h of n, and it was e to the minus 2 epsilon squared times n, and that was the right-hand side of the union bound for Herfting's inequality. We're now replacing the complexity measure with this, and if we know that's bounded from above with something that's n to the k minus 1, that's a polynomial in n, and therefore, choosing your data set size suitably, this is going to decay that expression to make sure that that probability is small. And that means most of the time, E in and E out will be close to one another, meaning that we generalize well out of sample. Does that make sense? Okay. So let me check the time. And I'm really surprised this worked because I never get it to work in the other room for some reason. So that's a good thing. All right. So from before, let's kind of demonstrate this. We've proven it, but let's further convince ourselves by demonstrating it with things that we've seen before. Okay. So with the positive rate, we said the breakpoint was 2, right? We can actually show with this formula upper bound on the number of dichotomies and actually validate that this breakpoint occurs. Now, we counted using an exhaustive argument where we took the function and we tried the function with a data set of size n, and we came up with a formula for the growth function n plus 1. Now, with this breakpoint, let's try this formula. If k is equal to 2 and we have a data set of size n, well, that means b of n 2 is equal to, less than equal to, the sum, I goes from 0 to 2 minus 1 is 1, of n choose I. Okay, well, what is that? Well, that's n choose 0 plus n choose 1. N choose 0 is always 1, plus n choose 1, that's n. That's 1 plus n. That's exactly the growth function that we had from before. Let's do that with the positive intervals. Now, of course, that's going to be breakpoint of 3, so that's going to be b of n comma 3, which is less than equal to the sum. I goes from 0 to k minus 1, 3 minus 1 is 2, and that's going to of n choose I. So that's going to be equal to n choose 0 plus n choose 1 plus n choose 2. So we have from before, this is 1, this is n choose 2 is what? N factorial over n minus 2 factorial 2 factorial. Okay, so n factorial is n times n minus 1 times n minus 2 factorial. These cancel, and so what we're left with, I'm going to kind of write up here, we're left with n times n minus 1, 1/2 times that, and that's going to be 1/2 n squared minus 1/2 n. Okay. And so we take this expression, 1 plus n, so we have 1 plus n plus 1/2 n squared minus 1/2 n. Okay, so that's going to be, I'll run out of space here, it's going to be 1/2, let me write it up here, 1/2 n squared, so that's 1/2 n and n, plus 1/2 n plus 1. And that's exactly what we had for the growth function of positive intervals. And so this last expression, and I won't do it for lack of space, but the breakpoint for the 2D perceptron was 4. When we got to a data set of size 4, it could no longer generate all 16 dichotomies. If memory served me, it was 14 dichotomies. And if we actually use this formula, well, we're just taking the expression that we have here, and we're adding plus n choose 3, right? And it'll work out to this expression. And we get this expression even though we never exhaustively came up with an expression for the growth function. Okay? All right. Any questions about this? So it is sound, it works, it is true, and now we have an expression based on a combinatorial argument based purely on the ability to generate dichotomies, plus 1, minus 1 labelings, to compare the relative strength of a learner, but more importantly, to determine whether or not learning is feasible. And so learning is feasible if the upper bound on our growth function is polynomial. Because if you substitute it back into the union-bound version of Herfting's inequality by choosing the data set size suitably large, you can decay the right-hand side of that inequality to the point where it's a very rare event for in-sample error and out-of-sample error to diverge from one another. Okay? All right. Does that make sense? Any questions? I wish I had a bigger tablet, and I'm really, really surprised that this actually works, because usually it doesn't work. All right, so with that, if no questions, that's all I had for today, and we will pick back up on Tuesday.